Here's part 2 of today's magnetism lecture. Make sure at this point that you access the lecture examples. I'm going to take you through those examples. Take a moment right now to copy down the first example. I'm going to give you an idea as to exactly what is meant by 1 Tesla. We're going to take a look at the expression F equals IL cross B. Okay, so this describes an experimental method of measuring the magnetic field B. A wire with a mass of 0.05 kilograms and a length of 1 meter is vertically suspended by a pair of conducting flexible leads while in a uniform magnetic field that is horizontal and perpendicular to the board. That then looks like this. Okay, so right here are basically 2 springs, these flexible leads like so. And then right here is the iron bar or whatever it is that's being hanging here or suspended vertically in this manner. Okay, the mass of which is given to us as 0.05 kilograms, and it has a length L here of 1 meter. And then the whole thing is hooked up to a battery. So let me just go ahead and put a battery here like so, with a potential difference V, and then therefore the conventional current I flows in this direction like so. Okay, now the whole time, this is all in the presence of a uniform magnetic field that's going to point into the board like so. Here's going to be B. Okay, now just in terms of forces, let's describe what happens here without the current flowing. Okay, so without the current, we just have the following forces acting. We have 2 tensions like so from these flexible leads as they're called. Just think of them as springs if you want, that's perfectly fine. So we have a tension here, we've got a tension here. Here's the iron bar or whatever it is. And then right here is the weight mg. So 2T is equal to mg because everything is just sitting there, okay? Okay, now what we do is we turn on the current. Okay, the current is now flowing through the circuit as I've drawn. Let me see what the numbers here are. And the current that is flowing through the wire here, I, is given to us as 0.5 ampere. Okay, however, this is enough current such that a magnetic force through IL cross B is going to occur upwards. Okay, that force upwards is going to cause these springs, if you will, to go slack back to their equilibrium position. So then therefore there will no longer be any tension vectors like so. Okay, so now the current flows. Okay, therefore, in this case, IL cross B is going to give us a force upwards. That force is applied equally at all points here within this iron bar or whatever it is. Therefore, mathematically, it acts as if it's applied to the center of mass. So right here we'll say is the center of mass of the iron bar, and then boom, right there is that magnetic force. Okay, now the magnitude of that magnetic force is just going to be ILB, and the reason for that is because we have a 90-degree angle here between IL and B like so. Recall that the magnitude of a cross product is in terms of the sine of that angle. Sine of 90 degrees is equal to 1. So then therefore the magnitude here of that force upwards is just ILB. So then therefore we just take ILB here, and we set it equal to the weight mg. So we basically have enough current flowing in the presence of this magnetic field to remove the tension associated with these flexible leads, these springs as we refer to them, and then therefore we no longer have those tension vectors, we only have the force vector upwards. And now we can go ahead and measure the magnetic field strength. So this is one way in which we measure the strength of a magnetic field. Like so, and now we just calculate. All right, so the mass is given to us as 0.05 and then times G, and then divide by I times L. So divided by 0.5 times 1. And that comes out to be about 0.98 Tesla, about 1 Tesla. So I set up this problem in this manner, so that this starts to give you an idea as to exactly what is meant by 1 Tesla. Okay? Okay, suffice it to say, you're going to see a bunch of early examples in the chapter 27 homework that deal with the expression IL cross B in much this manner. However, in this example, I'm describing IL cross B in terms of straight lines. What if you have some sort of curvature associated with a wire? what happens if the wire is not a straight line? So for example, that I have a wire that is shaped like so, and then we have a conventional current I flowing through it. Well, basically what I have to do here is I have to set up an integral. I have to picture the path here, the length of the wire, as being divided up into a series of infinitesimally small steps. So right here, for example, like so, is a little dl vector like this, and then let's say that we have a magnetic field that is present here into the board like so, B. It doesn't matter if it's a constant or not. Okay, therefore, what I can describe right here at this location is the infinitesimal amount of force that's exerted upon that infinitesimal length of the wire itself. I would do so by setting up this cross product. And then they get the total force that's exerted upon the wire itself. If it's curved in some manner, then obviously I have to integrate. That then gives me this expression here. Okay, for this expression, however, there's really only one type of problem that we have to worry about, and that's a problem involving what happens if a section of your wire is some sort of circular arc or some sort of circular loop associated with it. So now take a look at the second of the two of the lecture examples thus far. Okay, so in this example here, we've got this shape associated with the wire. Like so, where we have a current I flowing in this direction. Right here is a half circle with a radius capital R associated with it. And then for the straight line sections here of the wire, let's refer to this right here as an L1, say, and this right here as an L2. And then we have a uniform magnetic field that is present here. The uniform magnetic field will say points out of the page. So right here is the uniform magnetic field B, like so. Okay, now if you take a look at the straight line segments here of the wire, let me go ahead and put a current I here as well. If you look at the straight line segments straight line segments of the current itself, then we just have our cross product of IL cross B. So right over here for this section of the wire, we have IL in this direction, cross B like so, then it gives us a force vector downwards. Okay, that force vector, I'll call it F1, is I L1 times B. Same thing over here for this straight wire segment, we have IL cross B like so, gives us a force vector downwards. The magnitude of that force vector, call it F2, is I L2 times B like so. Once again, there's a 90-degree angle here between the IL and the B vectors. Okay, but what about the semicircle itself? Well, let's take a look right here at a small section of the wire. Right here in this direction, like so, is a little dl vector, and then we have the current I flowing in that direction. Okay, right here is the radius r of the circle, like so. Right here, let me go ahead and define an angle, theta. Like this. Okay, now, doing the cross product IDL cross B, in which direction is the infinitesimal force vector going to be? Well, I have here an IDL pointing in this direction, and then cross B like so out of the board. That then gives us an infinitesimally small force vector, DF, that's like this. It's inwards towards the center of the circle. On the diagram, it looks like so. So right here is DF. Here's what's critical. Break up that DF into components. We break it up into a component, I'll do it off to the side. That's horizontal on my diagram like so, and vertical on the diagram like so. Right here is the angle theta that I described earlier. Right here is a DF cosine theta. Right here is a DF sine theta. What happens to the DF cosine thetas when I go from this side of the diagram to this side of the diagram? Well, on this side of the diagram, without drawing it, the DF cosine theta on this side of the diagram would point to the left-hand side. it would cancel out this guy here that points to the right-hand side. So due to the symmetry here of the half circle, when you go from the left-hand side to the right-hand side of the diagram, the df cosine thetas cancel out. By symmetry. So then therefore, when I set up the integral, I have to add up everything just in terms of the df sine thetas. I have to add up these guys right here. So then therefore, the overall force is going to be the integral of df sine theta for that reason. Okay, this right here did not come from a cross product. It comes from breaking up the df vector into components and noting that the df cosine thetas cancel out and the df sine thetas add together. Okay, now how do I write this integral? Okay, well the df is going to be I dl b. Like so, there's a 90-degree angle between I dl and b. As I noted earlier, sine of 90 degrees is equal to 1. So there are actually two sines here in this calculation. This right here has a sine of 90 degrees from the cross product. This sine theta, remember, comes from adding up the components of the force vector that we need, the df sine thetas. Okay, now the dl. The dl is an arc length on a circle. Recall that angle is equal to arc length divided by radius. So then therefore arc length is equal to radius times angle. Let's go ahead and substitute that here. Like so. And now I'm integrating over the angle from 0 to pi on the diagram. Like so. Okay, a couple of things here are constants, the I, the B, and the R. So let's go ahead and factor it out of the integral like this. Like so. And now I'm going to go ahead and integrate my sine. So the integral of sine, let's see, the derivative of cosine is negative sine. So the integral of sine is negative cosine. So you pick up a negative sign here, be a little bit careful of that. From 0 to pi. Okay, now let's go ahead and plug in our limits. Oops, IBR. Like so. So when I do, I now have cosine of pi, which is -1, minus cosine of 0, which is also equal to 1. Notice the negative signs there cancel. Let's see, and yeah, this is correct. The negative signs here cancel, and I end up then with this. Let me group it like so. Notice that I put the 2r, the diameter of the half circle, in parentheses, because that 2r is just this straight line segment portion of the half circle, like so. So now add up all of the forces to get the total force exerted upon the wire. It's this quantity here, plus this quantity here, plus this quantity here. So let's just call that F total. So F total is going to be then I times B. Let's factor everything else out. Like so. So in other words, the wire behaves as if it is in fact all the way straight across like so, with this right here as its total length. So the half circular arc or a portion of a circular arc and so on, that's really the only calculation that we have to make here when setting up and evaluating this integral. Okay, I'm going to conclude here part 2 of the lecture. There will be a part 3. I won't be able to record it today. However, I'm going to have to record it very early on Wednesday morning. Today's shirt is a Monomarth.